Fabrication and established the Sensing Material Technology Lab. In 2004, he joined the Big Tech Labs in Bangalore, where he is currently working towards advancing the technology and manufacturability readiness of the indigenously developed medical diagnostic systems. His research interests include nanobiophotomics and nanoantenna.
All right, thank you. Thanks. So, good evening. As I was saying, unlike the previous presentation, not many images in this presentation, you have too many equations, bear with me. Okay, so this is basically on, how many of you are aware of fiber Bragg gratings? You know fiber Bragg grating, right? So you heard about coupled mode theory, right? And you know the equations for coupled mode theory, right? And usually you have to spend a couple of years before you can actually derive the coupled mode equations yourself from multiple books. What I'm going to do here is for your benefit. I'm putting all the equations here, including every single step without missing it. Okay, it's a basic mathematics, so you'll see a lot of equations, bear with me. If you have any doubt, please stop. So Bragg grating, the source comes from William Bragg, who actually used it to understand the crystal structure of materials. Basic physics is very simple. So if you have two layers of objects, two layers of materials, and you have an electromagnetic wave falling on both layers, the light beam that is coming from the bottom layer and the top layer actually have a phase difference between them. And if the phase difference is such that they constructively interfere, you get a reflection. If the phase difference between this beam and this beam is destructively interfering, you get anti-reflection. This is the principle of anti-reflection coatings in your optics when you do. You see when you buy an optical lens or something, it has something called ARC, optical anti-reflecting coating. This is the principle. So they make the thickness of thin film such a way that at certain wavelengths don't reflect back. Okay. So it ensures maximum reflectivity. You have seen fiber grating images, right? It actually basically is an index refraction along the core of an optical fiber. Not any optical fiber, we are talking about photosensitive optical fiber. Okay. So when you launch a band of wavelengths into this, depending on the periodicity of this grating, one particular wavelength comes back and the other doesn't come back. Okay. Depending on the pitch, you change the pitch, you can change the wavelength that is reflected back and what's been blocked here. It's basically a filter. Okay, it's like a notch filter. In realistically, you see the grating of this. This is your optical fiber, and you have grating somewhere in this. You cannot see the grating actually. Okay, it will be a part of the core of the optical fiber. The reason I gave you a picture is to show you the advantage of using optical fiber. This is your standard resistance strain gauge that is used to detect strains along one axis. You can actually have two gratings, two strain gauges. It can measure X and Y strains. Compared to this, you just put an optical fiber, it will do the same job. You can see the advantage here straight off. You have too many wires here, you have EMC interference coming in. Plus, in some structures, these wires are not preferred because of the added weight you are putting in. And you don't want too many, so finally you have one RSG, you have one more RSG, you will see combined RSG, you will see a trunk of wire. If anybody has a chance to go to Hindustan Aeronautical Labs, HAL Labs, LCA aircraft, that hangar, you will actually see a trunk of wires coming from the aircraft. So that's all resistance strain gauges. You can replace that with a single fiber. And the single fiber can have as many gratings as you can. So why does it reflect? As you said here, why does this structure reflect light? You are aware of Fresnel reflection, right? Fresnel reflection is a reflection of energy at any mismatched interface. In optical, you actually have a refractive index variation from one part of the material to another part of the material. At that junction, light reflects back. Bragg grating is similarly actually based on that similar. you have Fresnel reflection at every interface of the grating. That is what Bragg reflection is actually. Now, it is tailored such a way that Fresnel reflection from each of these faces is in phase. It constructively interferes. That's how you design. You design a Fresnel reflection that is in phase, constructively interferes. That is your Bragg grating basically. That's all. It's as simple as it. The same principle applies for two-dimensional photonics, two-dimensional photonic crystals, three-dimensional photonic crystals. Any optical structure is Fresnel reflection. Simple put out. So you can actually put a Taylor series to this Fresnel reflection. You can actually get out your reflective index. But that will come to that proper derivations later. So basically, you don't write gratings in a multi-mode fiber. You don't write gratings in a solid core fiber. You actually write gratings in a single mode fiber for a very simple reason. You actually have only one mode to work with. Every mode, when it reflects from the grating, it reflects in a different way. So if you actually write a grating in a multi-mode fiber, you'll see the reflection to be very noisy. You'll see many bumps, not single bump. But in a single mode fiber, if you write the grating, you'll actually see a very pure reflection profile coming back in fiber Bragg grating. So you can see the single mode fiber, multi-mode fiber, large core fiber. And when you launch a single mode fiber, you launch a pulse light, it comes out intact, ideally. But in this case, it spreads out, it loses some intensity. In this case, it loses much more because energy is dispersed into multiple modes actually. So we write gratings only in single mode fiber, and all theory we are going to study now is actually based on single mode fiber, not multi-mode fiber. Okay, this is the structure of your optical fiber. Typically, you have a core, cladding, buffer, jacket. Core cladding is silica, solid silica, with certain impurities in them to control the reflection index. Buffer on top is either PVC or polyamide. And the jacket, between the jacket and buffer, typically you will see a Kevlar strands actually. Have you ever seen optical fiber? You will actually see that yellow color Kevlar. That's the same material they use for bulletproof. It has got high tensile strength. And then on top of it, you have a jacket that could be rubber or PVC or polymer, anything it could be. So basically, our interest is write gratings in this part. So basically, if you have to write grating, you have to strip out all this. Expose just this. You can't remove this part. Only way you can remove that is by etching in hydrofluoric acid, 40% hydrofluoric acid. If you keep it for 55 minutes, you typically reach down to 8 microns actually. Okay. Have you ever done etching on the fiber? It's very simple. Take hydrofluoric acid, 40% concentration, put your optical fiber in that, and keep it exactly for 55 minutes, typically 55 minutes. By 55 minutes, you'll actually eat out all that 125 microns and come down to 8 microns. That's what we studied. You won't find this in any book. It comes through practice. Index grating. So this is what it is. Theoretically putting, you have an optical fiber, you have the core of the optical fiber, you have the refractive index grating inscribed it. I'll tell you how to inscribe this also. And actually, if you see, ideally it will be a sinusoidal signal like this way. Okay. This is your base core refractive index, and you have the average refractive index of the grating that is actually called N effective refractive index of the grating. Okay. Typical lengths of the grating, how long can the grating be? I've seen gratings as small as 1 mm, I've seen gratings as long as 10 centimeters. 10 centimeter gratings are very, very expensive because it's very difficult to make a 10 centimeter grating uniformly, having the same pitch along the grating. So don't worry about these equations. This is just showing how the effective refractive index of the grating is related to the core and clad refractive index. This is the equation for that. Okay, don't worry, we'll come to that. In practice, when you actually write a grating in optical fiber, if you see the transmission spectrum, that means you launch light and you are seeing this one. How does this actually really look like? It looks like this. You'll see that notch there. Okay, in this is a case where these gratings were written in IAC. These gratings actually have two gratings in a single fiber. Okay, and if you see this part, this one, that looks like this. Okay, and then you actually find this level. This is something like 28 dB, and then you find out what dB it is, and then you calculate the reflectivity. I'll show you that equation also. How do you calculate that? Okay. So let's do a very simple ray tracing mathematics on this. A very fundamental high school mathematics, nothing advanced. Okay, fundamental high school mathematics. You have one ray coming, reflects from the first surface. You have refraction, same ray reflecting here and coming from here. It is going further to one more layer, reflecting and coming from here. Simple. Okay. So what we have here is, what we want to find out is what is the phase difference between this ray and this ray, because this ray actually went through a longer distance, this ray went through a smaller distance, right? So this ray has accumulated some phase difference. So what is the phase difference between these two? That is basically we want to find out what Bn is, extra length it has not traveled. Very simple. So basically the path difference is n times Bc plus CD, and n dash Bn. Okay, this is n dash, this is n. Okay, that is a path difference. Bc is equal to CD. Bn is actually 2. This is fundamental geometry, tan theta, cos theta, blah, blah, blah. I'm not going to read through this. Basically, you will come down to this actually. Phase difference is actually what? 2 pi by lambda into path difference, right? Multiply that, you get 4 pi n lambda by this thing, cos, where this capital lambda is this pitch. Okay. Now, if you want this phase difference to be 0, that means when they're constructively interfering with each other, you actually have Bragg reflection. Just put theta as 2 pi and you actually get lambda equal to 2n effective. I'm approximating cos theta as 1 because I'm going to make theta is equal to 0, because in Bragg grating light actually comes against perpendicular, not at an angle, right? Fundamental. This is a very simple ray tracing algorithm, ray tracing equation, but this fails in many features actually. What we are looking at is a more advanced. You guys are masters and PhD, so you must be looking at some more advanced mathematics here. So what we are starting at is couple more theory. To understand this, first you need to understand certain drawing. You need to make a drawing first. The first drawing is that you have grating that is length L, Z0, ZL, length L. You have light coming in through this and light coming out from that. Okay. You have backward propagating ray, you have the backward propagating wave, you have the forward propagating wave. We'll come back to this multiple times, so you don't have to worry about this. Start with fundamental Maxwell's equations. I don't have to tell you, right, what fundamental Maxwell's equations are. Link the electric field, magnetic field E and B respect to the corresponding flux density D and B respectively. You know this, you have been through this so many times that it should be back of your palm, right? This we know, right? Permittivity, permeability. Permittivity, permeability are defined as so and so. In free space, vacuum, vacuum. And the material properties coming here. Fundamental. Interest is propagation of electromagnetic in a non-magnetic medium. We have mu r equal. So optical fiber is non-magnetic medium. We are actually coming down to what we need to do. So we are talking about optical fiber, which is actually non-magnetic medium. Okay. So we assume mu r is equal to 1. Next, the first Maxwell's rule. The vortex source of electric field is a time varying magnetic field. Del cross C is equal to dou B by dou T. Source of an electric field is a time varying magnetic field. That's what this equation says, nothing else, which we know. The source of time varying magnetic field is a time changing density of conduction and the displacement currents. You know about dynamo, right? Gauss law and all that. Dynamo. Rotate a magnet, you get current going. Create a current in a solenoid, you have a magnetic field coming out. This all comes from the same equations actually. Magnetic monopoles don't exist. That is, there is no source of a magnetic monopole, which means you don't see a south pole separately, you don't see a north pole separately. That's how it mathematically represents. Del dot B is equal to 0. Magnetic monopoles don't exist. The source of electric field is a charge. If you take a space, you have a charge in between, the source of the electric field is a charge. Basically, that's how you put in mathematics. This is your charge there. Assuming the electromagnetic field oscillating at single frequency angular omega, the field is represented as a simple equation, putting the real part here, the amplitude, and then you have the phase factor. So there is your simple electromagnetic equation. I'm only looking at time varying thing, I'm not looking at Z varying thing. We write the phasor expression. So we know phi. Now you put this E is equal to, E actually has the same form as this, H has same form, D has same form, B has same form. Same form as this. You have an amplitude, you have a phase. Okay. Using these expressions, we write these equations. We rewrite these equations. These equations. You have these expressions here, right? Put that in these expressions. You get this. We know this. That's most of the books or you read actually starts from here. Okay. Derive the electromagnetic wave equations or the Helmholtz equations. Apply the curl operator. You know the curl operator, right? Mathematics, high school, or BTech perhaps. Apply this to this on this equation. What do you get? This one. Where K0 is actually defined as this. And del square is called Laplacian. X squared, y squared, z squared. It's a Laplacian, three-dimensional Laplacian. You rewrite this equation now as this. I replace this part here. Okay. I just replace this one as this. Nothing much changed. Simplicity of this thing. Now, if relative permittivity is constant, the vectorial wave equation reduces to Helmholtz equation. So, if the permittivity of the optical fiber doesn't change over the length of the grating, which is true, we write it this. This is Helmholtz equation. Similarly, for K also you can write the same thing, same derivation. Okay, so you see where we started. Maxwell's equations, Helmholtz equations. Consider an optical waveguide which is uniform in the z direction. The derivative electromagnetic field in the direction is constant. Okay. That is what this mathematically says. That means along z, optical fiber is constant. There is no variation. I didn't put the grating yet, mind you. I am talking about simple optical fiber. No grating in that yet. I am going to bring in the grating now. I want to see a fiber without the grating. So along z, electromagnetic field direction is constant. Okay. Z component of wave number is k and defined as a propagation constant. Phase rotation per unit propagation. That is propagation constant. How much phase rotates per distance. That is propagation constant. This propagation constant beta encompasses many things. Wavelength, speed at travel, z, everything. So one symbol represents everything. That's the beauty of that. Ratio of propagation constant in the medium to the wave number in the vacuum is called refractive index, which is fundamental physics. Propagation constant to the wave number in vacuum is refractive index, effective index, right? Velocity of light in medium to velocity of light in vacuum. Or is it velocity of light in vacuum to velocity of light in medium? Which one is it? Refractive index. C by C0 or C0 by C? Highest, right? So refractive index is greater than 1 all the time. Typically in IAC conference convocation or something, your professor will ask you, do you have a situation where refractive index is less than 1? Okay. So we put that there. What did you put that here? This one. This is your Laplacian. Laplacian I am going to divide into two things. One is x and y direction Laplacian and the other is z direction Laplacian. Right? I am going to put this here. We know this now. Along z it is constant, right? This is x and y direction. I am going to take this and put it here. What do you get? This comes here. This equation, you see, this comes here, and this comes here, minus JB, and NFSK comes here. I am replacing the old equations from what I got, okay, from an optical fiber, basically. That's how these equations come in. Any doubt? Fundamentals. Similarly, same way you can actually derive H also. Same way. Neglecting the derivative relative permittivity. But what I mean by neglecting relative permittivity, this one I am going to neglect because permittivity won't change in optical fiber typically. We get the Helmholtz equations like this. This change to this go. You get this. Just this part and this part. This is Laplacian x squared y squared. Dou square by x squared, dou square by y squared, right? No z square here, mind you. You see the z square is gone now. Okay, the z square is in the form of this now. I removed the z square, that partial differential account along the length of the fiber. I have removed and replaced it with this. You see how it is changing, how the equation is changing. You see. Now take your optical fiber, introduce your grating, define something. So A is a forward propagating, B is a backward. A is a forward propagating, B is the backward propagating. One wave is going front, one wave is going back. Okay, the refractive index of the grating is actually is function of x, y, and z. Okay, actually it's only a function of z, isn't it? It doesn't change along x and y. But let's put x and y in z. Okay, right, and like the length of the grating is L. Now I want to see if A and B talk to each other. Do they talk to each other? In what conditions do they talk to each other? That is all I am talking about. B is caused by the grating, but I don't know. Okay. So what I am going to do is this: we write the transverse field components of fiber with the grating as a linear superposition of the counter-propagating modes of fiber without the grating. Understand this sentence properly. I am writing the equations of the fiber with the grating as a superposition, addition. Superposition is what? Addition of counter-propagating modes A and B of the fiber with the without the grating. What I am saying is, I will take an optical fiber, I will put two beams going opposite to each other, I will add them together. That is all I am saying. That is all the big jargon in English actually, it is very simple otherwise. Okay. So A plus B. You have the amplitude factor, you have the phase factor, simple. Minus B2 it becomes, because it is backward propagating, that is why it becomes plus, minus and minus becomes plus. So what I am saying is, I have one forward propagating and one backward, I am going to add them together, that is it. I want to see what happens when I add them together. In what conditions do they talk to each other? Ideally it won't talk to each other, right? If you have two light propagating optical fiber operators, they don't talk to each other. They won't, ideally. A and B are the slowly varying amplitudes of the mode E and X propagating the Z direction and minus Z directions with propagation going on B1 and B2. So I am also saying that not only that two rays are going opposite to each other, I am saying that they have got two propagation constant A, B1 and B2. They are not even same. It could as well be a red light and a green light. I am saying a red light is going this way, green light is going this way. Will they talk to each other? You know they don't talk to each other, right? I am just saying, I want to see in what conditions. I am not talking about the time here because I am not carried, I am only worried about the space, not the time. So I removed the omega t part. In the unperturbed fiber, that means fiber without the grating, this should satisfy the scalar wave equation, amplitude. Right? So it should satisfy, this is a scalar wave equation, it should satisfy, it should be 0, right? Okay. Is the refractive index profile of the unperturbed fiber, X and Y, no Z in that, remember. In the perturbed fiber, now you see perturbed, when I say perturbed fiber, I am talking about fiber with the grating. Okay. Infinity is satisfied, again, that also should satisfy the scalar wave equation. You have it here. You see what I did here? There is only n square x here, but I brought in n square x, y, z. Because there is a perturbed fiber, I am introducing the grating now, mathematically. That is your grating. I just introduced it. Now, practically speaking, what did I do? I fabricated a grating in the fiber now. Mathematically, I put this equation, n plus n cap square. So this one plus this one. That's what I did. Again, this Laplacian I split into two. You seeing that? Laplacian I am splitting into two. The x and y component, z component. Z-timid refractive index profile of the grating with the fiber with the grating. Now put this one into this. We know this original equation, right? E is actually A plus B. Forward propagating, backward propagating. Put that E into this here. Solve that equation. You get this. Don't worry, scary, forget about it. When you actually take a newspaper and write it, you will actually get it simply. It's very easy actually. It's straight mathematics. There's nothing great mathematics here. I am going to assemble, collect these common terms. I am going to bring these together and bring these together to get this. That's all I did. Collected the terms together. Now you see what I am doing here. Dou square by dou z square of this one, I expanded into this. I actually expanded it. Partial derivation of some function, I am expanding it here. Same way for B also expanded here. I didn't do anything, right? I just expanded this one to this one to this. You got this equation. You rearrange again. Just rearrange. I am not doing anything here. Why I am rearranging, I will show you. Because I am going to collect these terms and these terms together. Why? Because we know that is 0. That is 0. You get this, just this term and this term remaining, that's it. This scalar wave equation. You just remain this term, you remove this term and this term. We know it's this thing, and rearranging. Now we use actually slowly varying envelope approximation. This comes often in people who actually work in optics. Okay, slowly varying envelope approximation. What slowly varying envelope approximation says is that the envelope of the signal varies slower than the signal itself. That means the amplitude, the general amplitude of signal does not vary in a small length. Signal can vary, but the amplitude won't vary. The envelope won't be varying much. That is an approximation that makes life easy. Okay. So basically, what it means is this is negligible compared to this. So basically, you take your original equations and remove these parts. You get this equation. Slowly varying envelope approximation. Okay. So that is what SVEM means. You see that in every optics subject, you will see that. Remove this part, you get this. Introduce the term this, so that mathematics is easier, your calculations are easier, just making life simple by using one single notation for instead of other notations. So, but divide the entire thing by e to the power of b1z, okay, get that. Now, orthogonality condition is what we are going to apply now. This is where it comes actually. We are going to say that only modes with same order will have non-zero overlap. What do you mean by non-zero overlap? That means when two modes, similar modes interact with each other, the sum is non-zero, means you get something out. Technically, there is no way otherwise putting it actually. Technically, you will actually say that if you add two modes that are not identical each other, you will not get anything. You can't say that in technical. Technically, you say that identical modes when they overlap, you get non-zero overlap. In mathematics, you say non-trivial solution. Okay, it's not trivial. So that's what this means. You apply this one here. You have this equation, multiply the entire equation by this and integrate. Entire equation. So you multiply this by this and integrate along dx and dy. Entire equation. Rearrange this equation into this. That means basically I am bringing this negative part to the right side of this and keeping it this side. Only the positive part is this side. This one is equal to this one. I just rearranged it. This is the equation. Now you see this. I am just dividing this equation by this, dividing this entire equation by this factor. So this factor comes down here, this factor comes down here, this factor comes down here and goes there. I am just rearranging, I am just isolating this guy out, dou A by dou Z. So bring everything to the right side. Rearranging. Similarly B also, rearrange everything. So you have these original equations. Now are you noticing something here? This is your coupling coefficient K11, K12, K22, K21. You see these equations in your literature typically when you take a paper out. Bragg Grating introduction is actually, they say dou A by dou Z is equal to J coupling coefficient, this is where it comes from. These how coupling coefficients are derived. This is your coupling coefficient. This is your, actually many books start at this point for Bragg Grating. They don't talk about this, rest of the part. So you have your grating now. So what we are going to do is we are going to define x, y, z. So n, x, y, z is actually x square by this sine. So I am going to assume that your refractive index profile is sinusoidal for now. Simple sine signal, sine, simple sine. Ideally it is not, okay. So I am assuming it is a sine with a periodicity of capital lambda, 2 pi t by t, right? That is signal of your sinusoidal signal of frequency f 1 by t. So in space, instead of t, put z and the pitch of your grating. Okay, simple, single. This is where it comes. You see that n square. Keep an eye on that. All right. You see what I have done here. What was this before? Cap. N cap squared. What I have put here? Tilde. And tilde square, because that z factor has come out. Z factor has come out. Put the z factor out and put it rewrite it like this way, k1, k1, k21. So now this equation becomes like this. To evaluate the contribution of each terms on the right hand side, we integrate over the length. What do we integrate? Basically, you are doing it, find out the actual output. You want to find out the output of something, you need to integrate under the curve, area under the curve. If you take a photodetector and you pump in some wavelength of light, you will see a response of photodetector, right? But how do you know what is the actual output? How many watts you need to tell? Integrate under the curve. Okay, area under the curve gives you the output wattage, basically. Similar here, you have two lights propagating, you got an equation out, you want to see the total output, integrate over the length L. Minus L by 2 to plus L by 2, integrate over the length. Now you see that as capital K approaches delta beta, the contribution first terms and second term become negligible. This basically it says that as your wavelength of your light, you are pumping into the optical fiber, reaches a factor of the pitch of the grating, you will see that some terms disappear. That's what it means. What I'm saying is, your Bragg grating is designed to reflect 1550 nanometers. If you are pumping light at 1545 nanometers and from 45 nanometers increasing wavelength to 1550 nanometers, you will start seeing the reflection increasing. That's what it means. These two terms go, you actually are left out with this. We retain this term and you have this part here. I'm just replacing some more simple symbolism actually here, this one. So basically for B also you get the same way out. So this is orthogonality condition saying that only two identical modes talk to each other. Non-identical modes don't talk to each other. That is orthogonality condition. So you can actually replace these two by a common factor. Now I'm saying that the forward propagating wave, what this statement means is that the forward propagating wave and the backward propagating wave are similar. Now I'm bringing the condition where they're going to talk to each other. Until now they are not talking to each other. So you replace this with K. Just replace this two with K. Simple, life becomes simple. Now for Bragg condition to satisfy, you have that this should be 0. What is this? You know what this is, right? This should be 0 means delta B is equal to K. You see they are going to approach to each other. So this becomes 0 means delta beta is equal to capital K. Basically forward propagating wave and backward propagating going to talk to each other. They are identical to each other in phase, in wavelength. The difference in the propagation constant of the two contra propagating modes must be equal to the spatial frequency of the grating. Suppose the forward propagating wave and the backward propagating wave are such that they have some multiple of the pitch, you actually get the Bragg condition. So just put it that here, beta 1 to beta is equal to this one, that means K is equal to 2 pi by lambda implies that lambda B is equal to 2 an effective pitch. This is a Bragg condition. This is where it starts. Okay, differentiate and then at pitch is equal to, that means Bragg condition. At Bragg condition what happens? At Bragg condition this is what happens. Differentiate this and put gamma is equal to 0, you get this. Non-oscillatory solution. So what is the solution of this partial differential equation? Basic mathematics. Dou square x by dou b square is equal to k square something. What is the solution? Non-oscillatory solution. You know this, right? Basic solution of a partial differential equation, mathematics. So this one goes here, you get A out. Put this solution here, you get A out. So now you have B, now you have A. So forward propagating is now given, backward propagating is now given. Come back to the original image. At Bragg condition, look at this, it is always at Bragg condition. Unit power is incident in the mode at 0. That means I'm going to launch the light from this side of the fiber. That means I'm launching 1 unit power from the reference 1 normalized. Okay, at Z is equal to 0. At Z is equal to 0, I'm going to call it Z0. At Z at L is equal to ZL. So A at Z0 is equal to 1. That means I'm launching the light at the optical fiber from this side. There is no back propagating wave beyond. So all light reflects from here. So this backward propagating light starts at this point, right? There's nothing after that in grating. So B at ZL is equal to 0. So at this point B is 0. At this point A is equal to 1. This is called boundary condition of the grating, mathematically speaking. You see what is happening. I'm actually doing an experiment, right, through equations, right? Now A and B, we know the original equations. Okay. Now you put the boundary conditions in this place. So to B ZL is equal to 0, 0. Z equal to L if I put, Z equal to L if I put B at L becomes 0 and A at L becomes 1. This comes here, this comes here. Boundary conditions are applied. Now we find rho 1 and rho 2. Find rho 1 and rho 2. How do you find rho 1 and rho 2? Do you remember these relationships? Cos h and sin h, hyperbolic sine, hyperbolic tan. These equations you know, right? Put that equations here. Where? Here. Rho 1, rho 2 can easily find. Rho 1 is equal to 1 plus rho 2. Put that 1 plus rho 2 into this one is equal to this one, rho 2 you get. Put the rho 2 back here, you get rho 1. Put that here, you get A and B in the t to the power of form. You use this relationship, A and Z become like this. Many books starts from this point also. A is equal to this one, B is equal to this one. Okay. Now the reflection coefficient. What is reflection coefficient? B by A, forward propagating wave by backward propagating wave. Sorry, backward propagating wave by forward propagating wave. That is your reflection. So what becomes cos by sine, sine by cos becomes tan h. Reflectivity, magnitude of it. Magnitude of it. This also you see in literature, right? This is how it comes. Now what happens what happens to the signal when the Bragg condition is not satisfied? How does it look like? What happens to it? At Bragg condition is solved, right? Now for not condition, what will you see? So differentiate this to get this. We differentiate this guy, you get this guy. The characteristic equation, you know what is the equation of a partial differential? You get the characteristic equation, right? You guys have passed all gate exam and all, you know all this. So get the characteristic equation. Roots of the characteristic equation are so and so. From the quadratic equation here, you get the roots. This is what is the Bhattacharya equation or something actually. That quadratic equation x squared plus 2ab plus something, right? That's actually Bhattacharya solution. This one. Not many people know about it. Okay, the basis functions are for this quadratic equation. Basis functions are so and so, and the general solution A is equal to like this. So you know the characteristic equation, basis solution. You know this mathematics, right? This is high school basically. A and B is equal to 3. After that, solve for U and B. Again, apply the boundary conditions at this. That means source is at a 0 and no reflection after the grating. Put that here. You solve for U and B. Solve for U and V. U is equal to this one, V is equal to this much. If you do this mathematics, you will get this. It's very simple. Reflection coefficient R is B by A. Again, B by A. So put take the what do you call take the ratio of these two, B by A. R is equal to so and so. You know that where I replace some equations by gamma, so as life becomes a little bit simple. Okay. Using the representations of sin h and cos h again. We have the reflectivity R is equal to magnitude of this as this. Again you see this in literature, right? Same thing. You have any question? I can give you these notes in case if you want. Reflection coefficient R is a function of the detuning parameter. So basically what I am saying is I want to see reflection when my launched light is not equal to the Bragg wavelength. What happens when the light that I am launching into the fiber is not equal to Bragg wavelength? So I am going to put a variable delta to that. So I want to see how reflectivity varies as a function of delta. So as delta is equal to 0, you get the maximum reflectivity. That means that is a Bragg condition, lambda b. Okay. So delta is equal to 0, gamma is equal to, put that here in this equation, you actually get R max is equal to tan square. Determine the variation of reflectivity around this thing. So with very close to the Bragg condition, you have this reflectivity. Far away from Bragg condition, this part gamma becomes imaginary. This gamma becomes imaginary. So reflectivity comes in this form. Now sin h is gone, sin square comes. Okay, you know the reflection between sin ix and sin x, right? Sin h it becomes. R is equal to this one. When R is equal to 0, when this factor is a multiple of pi, 2 pi and 3 pi. First 0 on either side of delta occurs when this is actually pi. Put that here, you get lambda as capital gamma is equal to like this. Gamma is actually defined as this. The bandwidth of the reflection. This actually gives you the bandwidth of reflection. So delta B, now you bring everything back this side and put this factor here, you get this. This is the bandwidth of reflection. Let me pictorially show you what it means. You know the reflectivity of the grating looks like a theoretically simulated, right? This theoretically simulated looks very clean, symmetric from at 0, looks both sides same. So as the length of the grating increases, what happens? Reflectivity increases, but this also becomes wider. That's what this shows actually. So very small length of the grating is here, but reflectivity is also very less. As length increases, reflectivity increases, but the full width tap maximum also increases. What I mean to say is this. This is a region around the grating, mathematically speaking. This is a region away from grating, mathematically speaking. That's the equations we brought an equation for this, we calculate the equation for this. So you get your first zeros at this point. That's what I'm saying. This is the width of the grating, that equation we just derived. That is the Bragg condition. This is the equation of the entire spectrum. So basically if you put this into your MATLAB and vary z from some number to number, you actually get this drawing, this graph. This is how the equations are derived actually, from base to this point. Okay, you won't see this in any book. Fabricating grating. What do you need to make a grating? What do you need to make the grating? You want to make the grating in your lab, what do you need? I told you optical fiber is basically what? Photosensitive optical fiber. When I say photosensitive optical fiber, I'm talking about germanium doped optical fiber, okay, or boron doped, anyone, okay. Typically any optical fiber you take, normal communication optical fiber you take, it has got some germanium in that already. You cannot remove that germanium impurity from the what do you call that that nugget, silicon nugget actually. When they purify the silicon to draw the fiber, the preform that looks like a tube light actually looks like a tube light preform. When they purify that, you cannot purify it 100%. You have some quantity of germanium in that. So what they do is actually increase the level of germanium, and when you have germanium maximum, it absorbs certain wavelength of light. Typically 243 to 248 nanometer light it absorbs, UV light. That's UV. And when it absorbs light, it refractive index changes. So for that you need a UV source, right? Examen laser typically, krypton fluoride examen laser. Okay? You need a shutter, because I'll tell you why you need a shutter. Examen lasers, when you switch it on, it takes 2 hours to stabilize. Intensity and wavelength has to stabilize. So when you write a grating, when you don't want to write it, you cannot keep switching on and off your laser. You never ever do that. Keep a laser on always. Come in the morning, that's what I used to do. Come in the morning at 9 o'clock, switch on the laser, it's on till evening, until I finish. I only use a shutter to close it on and off, that's it. Shutter opens and releases, that's it. So a shutter, it's a mechanical shutter. Wavelength has to stabilize. Then you need a lens stage. What does this lens do? It's a cylindrical lens. It focuses along one axis. So light coming into cylindrical lens is focused like a line, like a tube light, like a line. Okay. That should fall on a phase mask. A phase mask is the one that creates a diffraction grating. Okay, that grating basically you want to write N1 into N1 into. So you need high intensity, low intensity, high intensity, low intensity. So you need something to create the interference pattern basically, right? Double slit will give you minimum. So if you have multiple slits, you will get multiple refractive index patterns. So basically you need a phase mask. Phase mask, I'll show you what it is. That's what it does it. Put the phase mask, put the fiber there. Ideally it is recommended to hold the fiber using a vacuum, because if the fiber moves a little bit, we are talking about lambda b is equal to 2 n effective pitch. If lambda b is 1550 nanometers, assuming n effective is 1.45, 1550 by 3 is approximately 570 nanometers. So you are writing a pitch that is 570 nanometers variation. Even if you breathe on the fiber, when you are writing grating, you erase the grating. It is that sensitive to movement. That is the reason the whole system is on a vibrational acceleration table. It has to be lifted, levitated, then only write the grating. In my experience says that when you actually write this, even if someone stomps next to your experimental setup, you will see that grating has become wider. It's very sensitive that way. We used to have a window AC, that old generation window, Volta says makes sound. Okay, that vibration used to come here. So we had to switch it off, do all. So it's very, very sensitive. In any advanced lab, interference based experiments are in the basement, not even in the ground floor, and never in the first floor. Should not be, ideally. In any advanced lab, if you go Stanford, MIT, you will actually see underground the lab is. Underground, no vibrations are coming there. Okay. Then what do you need? You need a motion isolation. This microcontroller. What does the motion controller does is actually it brings the fiber very close to the point. Why I am telling you? Because when you have the cylindrical lens focusing like this, when you have a cylindrical lens focusing onto the fiber through the mask, so a cylindrical lens looks like this way. Cylindrical lens looks like this way, okay, and then it focuses like this as a line, okay. Now this actually passes through an optical, this passes through a phase mask, and then you have diffractions coming. You need to put the fiber exactly at the focal point, right? If you put it, let's say it's blurred, gets blurred, the index gets blurred, so you have to put it here. So basically you need to have very good control along this direction. That's the reason you have a motion controller that is actually close to 0.1 micron resolution. Actually you need better. So basically you bring the fiber in and out and see where the exact focus is. You get the best grading at that time. So this requires lot of alignment actually. Even if this guy is tilted little bit, suppose this guy is tilted, the cylindrical lens is tilted, it's blurred completely. So this is how it looks like when light comes from this side, from the face mask is this kind of structure, it's like a surface structure. The entire thing is transparent, by the way. So basically the way it functions is this one. The functions like this. When light passes through this, the distance traveled here and distance traveled here are different, right? So this one accumulates a phase difference. That's the reason it diffracts. This way, it diffracts this way. And in the overlap region, you have the grating. Fundamental physics. So basically you tailor this thickness. T1 and T2, you tailor that. And even you tailor this one, pitch of the phase mask. That decides the refractive index pattern. So basically this, when light comes out through, you have first order, second order coming here, first order, second order. Phase masks are designed to enhance the first order and minus first order and to suppress zeroth order and higher orders. You don't want that, okay, you want first order only. So if you look at the light at this point, between the phase mask and the fiber, it will look like this. This is called Bragg pitch. 2 pi n effective pitch, this is the one. And this is called Talbot pitch. Okay, it's called Talbot pitch, this is called Bragg pitch. You won't see this in any book, I think 1 or 2 books only mention this part. When you see the refractive index, if you simulate the refractive index at, the intensity distribution after the diffraction here, it looks like this. It looks like a egg tray. You have the egg tray, right? It looks like that. So you put if you put the fiber here, you'll pick up one of these, right? That's all. So you put the fiber here, you pick up this. You put the fiber here, you'll pick up this. You still get the Bragg pitch. But when you move the fiber like this way, you're moving from a low intensity to higher intensity. You're actually raising the grating. So this, while writing the fiber moves away, you're gone. No grating you get. So it looks like this under a microscope. High power microscope. So this is what it is. So if the pitch of the grating, pitch of the phase mask is lambda pm, pitch of the grating is lambda pm by 2. Simple. So basically, if you want to find out what is the reflectivity, what wavelength you get, just put this pitch of your grating there. Pitch of your phase mask there. When you actually write the grating, how does it look like? It looks like this. In time, this is close to 5 minutes. This data is 5 minutes data. So I captured every few minutes. I captured the grating spectrum in the optical spectrum analyzer, and how it evolves over 5 minutes. So it evolves very simple, like this, and then it starts moving. So at some point it starts coming down, and before it comes down, you stop it because they get the highest reflectivity. If you keep writing, it will erase it off. It will just erase the grating. So not only time based, not only distance based, you also have to make sure your timing is perfect. So you actually have to keep eye on your optical spectrum, and you see the grating growing. Moment it starts coming down, switch off. Close the shutter, switch off the laser. You got a reflection. This is how it looks like. That's one. Second thing is basically it's intensity dependent, it's also time dependent. So if intensity of laser is very high, you get type 1, type 2, type 3 gratings, right? How many types of gratings are there? Anybody can tell? Type 1, type 2, type 2A, type 3. There are actually 7 types. Type 2N, 2N plus 1, 2M, many are there actually. Okay? Now, even if you change the fiber material, suppose you buy Stockerel fiber, you buy a Newport fiber, same writing conditions, I mean different fiber, same writing conditions, you see the rate at which the refractive index changes. The rate at which it picks up grating is different. So when you even change the fiber, you'll have to tailor your writing parameters to get the right reflectivity. This goes slowly but goes farther. This goes very fast but immediately falls down. So you choose your grating based on your fiber. So it's very important that when you make a grating, you stick to one vendor. Stick to him, always get the same fiber from him, or buy a long fiber at a time. Okay. When you write 4 gratings in a fiber, this is how it looks like, 4 different gratings, and this is 97, 97, 93, 96. This is all written in IISc here, instrumentation department. This is how you calculate reflectivity. You find out this drop, delta P, find out this delta dB, find out this dB, find out delta P, put this in equation, that is your reflectivity. Good question. So why does reflectivity reduce when you continuously keep writing it? I'll explain that because some explanation, explain back to that, okay? Let me complete this part. So now look at the sensor. Lambda B is equal to an effective pitch. So if you have grating, if you just pull it like a rubber band, the grating spread out. So basically the pitch will change. So basically that's how you change. This can either change because of strain or temperature, expansion or pulling. So you have a function of strain, you have a function of temperature, delta L, delta T, differentiate. And then you have the sensitivity. It is 1.2 picometer per micro strain. This is mu E, sorry about that, this is not mu M. This 10 picometer per sensitivity. That is typical sensitivity of optical fiber. Okay. Now the advantage in single optical fiber is that you can write strain sensor, temperature sensor, pressure sensor, vibrations, chemical concentration, everything. You can write everything in one fiber. One fiber can have 10 gratings, 10 different parameters. That is the beauty of fiber grating. This is a big thing in GE nowadays. General Electric, Eaton Corporation, and even Schlumberger. So what they do is they have this optical fiber Bragg gratings that actually go into downhole of the oil drill actually. You have this sensor that are actually packaged to withstand close to 900 degrees and close to 5000 microstrains. And normal optical fiber cannot withstand 5000 microstrain, it will break. So you actually have high strength optical fibers that can actually withstand 20,000 microstrain. So it goes down into the bowl, almost close to 1 kilometer down, and then senses the temperature, pressure, gas sensing also is done, humidity sensing is done, and I think vibration sensing is done. This is actually a current ongoing project in many of these companies. So fundamental equations, simple. The difficulty is not the mathematics, difficulty is engineering actually. Okay. Suppose you put 2 identical gratings on either side of a cantilever and move the cantilever up and down, what will happen? One is getting compressed, one is getting pulled, right? So you get this, so these guys move out and in and out, in and out. This is what we did here. So you can actually see the slope, 1.228 picometer per microstrain. Strain, you know how to calculate, right? Delta L by L. It's very simple. So you have seen this picture, how it compares to. So this is a temperature sensor. We put it in liquid nitrogen. So we went from minus 140 to 140, plus 140. Negative and positive, very, very linear. One experiment we did that we kept the fiber at 600 degrees for 16 hours overnight. Held at 600 degrees, 16 hours. The reflectivity decreased actually, so it deteriorates. So normal optical fibers will deteriorate at temperature that are close to the TG of your fiber material. Glass transition temperature. If your temperature close to glass transition temperature of fiber, it will deteriorate. Magnetic field sensor, very simple, put it on a nickel or any microstrictive material, change the magnetic field, it will strain sensing, and then it does magnetic field sensing. Current sensing, IR square heating, basically based on the current that heating will change, you make very, very simple fundamental sensors actually. Chemical sensing, remove the cladding, as I said, put in hydrofluoric acid for 55 minutes, you will see that changing. You will expose the grating, cover the grating with certain material that is sensitive to some chemicals. So when the material is exposed to that chemical, it refractive index changes, changing the wavelength of light. So this is the ethanol concentration sensor. You can even write Fabry-Perot cavity. You know Fabry-Perot, right? Fabry is basically two ettalons, mirrors in between cavity. You can actually write gratings in fiber also. So you just make sure that this part is blocked when you write the grating. Block that part. You actually write grating on this side and this side. You create a Fabry-Perot. So you get this typical free spectral range, FSR kind of rings, right? Same thing you get here. You can control this by defining. Actually, what we did, this, you know how this was made. This is very simple, very improvised thing. This is like they said Jugaad, right? So one professor came from IIT Madras and told, Madhav, let's try Fabry-Perot. How do you do that? So basically you need to create two gratings that have got exactly nice thing. I said that $10 will take time because we need to purchase that. Each one is like 20,000, 30,000 rupees. What do you do? I want to know what will happen now. Simple. I just took a staple pin, flattened it out, made a small fixture and blocked the light there. You saw a shadow there. Got the grating, got this. Stapler pin is very well controlled dimension. Stapler pin, by the way, you take it for granted, but it's very well controlled. The dimensions in few micron correction it is. Now then we understood. Okay, we can do this. Then we perfected that. We put an optical fiber itself as a block, 125 micron block, and we tried many variations. We used it as a sensor. We got very good data on this. So that is the output of this talk. Any questions? That's the last part. Now you are asking, why does the grating change? You are asking, why does this happen, right? Where is that? Why does this happen, right? Have you noticed one thing? You see side lobes only on this side. You don't see side lobes on the other side. Same here. You see side lobes on this side. You are not seeing side lobes on that side. This is very common in optical fibers. Not your ideal theoretical that you have side lobes and ideals very beautifully on both sides, like sinc squared. You know, you take sinc and you square it. What you will get? You get side lobes on both sides, right? But why? It's like you have a sinc signal. You square this, you get this, right? Sinc squared. But in optical fiber you actually won't see that. You will you'll see it like this. So on this side. There's a very simple explanation for this. Your laser output, light that is coming from the laser, yeah, if you see helium neon laser spot, if you take across this point, you will see light is like this way. Intensity is like that. It's Gaussian. It's not flat top, right? It's Gaussian. Now, when you have a Gaussian light, you are creating a grating pattern, interference pattern based on Gaussian light, like this. You are creating interference pattern. So intensity is very high here, very low here, right? You are creating intensity pattern basically. So what you are going to see is this. Intensity pattern of interference signal. Interference pattern. If you take the intensity profile, looks like this, right? This is where fiber is this fiber core is exposed to this. Now see what happens. This section where the intensity is high, grating forms first. It forms first. Quicker, faster. This section grating forms later. This is weaker grating. Okay? So now what happens is that you see what happens. Now this intensity is less. Okay, you have grating that is forming at lambda b, but in a different spectrum. Continue exposing this. This grating is already maturing. What happens is that when you see the spectrum, it starts initially like this way. You know why this forms like this? This lambda here and lambda here are slightly different. Because the contrast of the interference pattern here is poorer than the contrast of the interference pattern here. So basically the pitch is slightly different here and here than here. Okay, so this wavelength is different, this wavelength. So what you have here, you have a Fabry-Perot here. You have a Fabry-Perot with this wavelength here and this wavelength here with a cavity. Light doesn't see it anyway because the wavelength is different. You have a Fabry-Perot. This is output of a Fabry-Perot. Now continue writing. Over time what will happen is this guy forms quicker and it jumps out. So this guy moves out. Whereas this guy is still forming. So basically it forms like this way. He has moved out. Continue writing. This guy will move out. So basically he will end up like this. He has moved out. The center part has formed first and moved out. Outer part is still forming. Continue writing. What will happen is it actually heats up the fiber, generates heat. When you generate heat, actually you actually destroy the refracting disk grating. Actually make it blurred a little bit. So this guy starts falling. So it falls, falls, falls. See, this guy is still increasing a little bit. You see that animation. You see this, and this side, this guy is still increasing. You see? See? Increasing, falling. This guy will fall before this guy even starts decreasing. So this is the effect of your laser intensity, nothing else. Now, typically when you go to your comprehensive or defense, your professor or examiner will ask you, what controls the full width half maximum of a grating? Can anybody answer? What controls the full width half maximum of a grating? You know the equation of full width half maximum? This one? So what controls it? What are the factors that you can play with here? L and effective. You can play with it. So if you increase the length of the grating, your full width half maximum will become smaller. Is it true? If I have a 1 centimeter grating, if I have a 5 centimeter grating of the same pitch, which will have the lesser full width half maximum? Neither. Trick question. It's not A or B, it's neither A or B. I'll tell you why. Full width half maximum is a function of the what you call the purity of your laser. The purity of your laser, the purity or the contrast of your interference pattern that actually writes the grating. Higher the contrast, purer the writing, right? What is, okay, this is fundamental signal processing. Let me ask you something. I have an infinite sine wave, single frequency. What is the Fourier transform? What is the Fourier transform of a sine wave? Delta function. It's some frequency, right? This is a frequency. What is the Fourier transform of a rectangle pulse? Sinc. What is multiplication in space domain or time domain? What is it here in Fourier domain? Huh? Huh? What is multiplication of S? Multiplication in time domain is what in Fourier domain? Convolution. Correct? Convolution of these two, what will it give you? It will give you sinc at that point. Understood? If you multiply these two, what do you get? You get a grating. That's what you are seeing. This is in this thing. You just take the magnitude, you get this. That is your grating. Reflection spectrum of a grating is a Fourier transform of a sine multiplied to the rectangle profile. Now, unfortunately, your laser is not like this. Your laser is like this. Now you do the math. That is your grating. There's nothing different in this. Very simple. I'm not drawing that imaginary part of this. Okay, we will have one more here. But this is mathematical convenience, not the reality. So you will see the same thing here. But I'm not worried. We are already about the real part, right? That is what grating is. A truncated sine wave, inverse Fourier transform is a reflection spectrum. Remember that. Reflection spectrum of grating is a Fourier transform of a truncated sine wave. Simple. Now, if you question, now I multiply with this, I multiply with this, what will happen here? I multiply with that, I multiply with this. What happens there? For this, you will see it like this. Right? What about this? What will happen here? This is what is going to happen. Sorry, this is black. Okay? Green is going to be like this. Thinner. Thinner. You make it even wider. This will become even more thinner. Thinner and thinner. So initially it was like this way, it will become like this way now. Even wider, if you make it, it will become like this. If you make it infinity, you get a delta function. So what does it tell you in grating terminology? If you increase the length of the grating, your reflection spectrum will become thinner and thinner and thinner. That's all. Mathematics. There's nothing great science here. You need to link multiple subjects together. That is where your effectiveness comes. Signal processing to optics. Link it. You will see many similarities. That's what this is. Longer grating, tighter this thing. Smaller grating, wider the signal. You remember your signal processing. Simple. That's all it happens here. Now, did I answer your question why it moves out? Because of your intensity profile of your laser. Why do you do, when you do signal processing, why you always assume in noise as Gaussian noise? Why? White Gaussian noise. Signal processing, what is it book, big book? Digital signal processing. Huh? What is it? Tell me. In that, if you see is noise analysis of your transform, what is that? Noise analysis of your transfer function. You have A, you have transfer function H, you get Y, X, H and Y, then you put X plus add white Gaussian noise. Why Gaussian noise? Have you ever questioned your lecturer why you want to add Gaussian noise? Why Gaussian noise? Why not other noise? Poison is also used, but why Gaussian? I understand. Poison is used, uniform noise is used, many other noise matters are there, white noise is used, whatever. But why Gaussian noise? Very simple reason. This is in nature, if you make a recording of any noise, in nature, if you make a recording of any noise, it's Gaussian in nature, in profile. Any noise you record is Gaussian. And when you put a Gaussian through any transform function, output is Gaussian form. The form doesn't change. Even when the Gaussian noise goes through any system, any filter, any electronics, anything, output is again Gaussian in form. It might change in the density distribution, but it's always Gaussian in form. So form is preserved. That's why they try to test the transfer function of any system using a Gaussian noise. Simple. What changes? Form won't change, but what changes? That's what they want to understand. That's why Gaussian. Second, you know central limit theorem? What is central limit theorem? You heard but forgot. Central limit theorem is very simple. If you have one signal that is distribution like this way, you have suppose uniform noise distribution. You have another signal that is again uniform noise distribution. Like that you have 100 signals with uniform noise distribution. You add all of them together. The sum is Gaussian. The sum of non-Gaussian in signals is more Gaussian than the individual signals itself. No, add, just add. It becomes Gaussian. So everything tends towards Gaussian in nature. That's why you do Gaussian. Why I mentioned here is because our light source is Gaussian in profile. Light source is Gaussian in profile. So that will preserve here, that will come up here. So have you seen the refractive index of the actual grating, how it looks like? It looks like this. Reality. You have a DC factor, you have a AC factor. DC coupling coefficient, AC coupling coefficient. You have seen these equations, right? So you have a DC factor envelope, you have an AC signal. This is how it looks like. Why? Again, see Gaussian coming up. This is your grating. Anybody wants notes, I can give you. Okay. Thank you. Now, this equations which you are seeing, lot of equations are there, may be difficult for you to memorize. These equations exist in my thesis, which is available to download on IIS, you know that. So you can just download, you can see the equations. Even minute equation steps which are not shown here are there. Complete derivation in one place, you won't see anywhere else. So just have a look, you'll have it. Actually pump these equations to MATLAB, you get your simulation. It's very simple. Same equations are used to derive even transfer matrix model, TMM. Same thing, nothing different. All right. Thank you guys.